In this experiment, we're going to be trying to find the comparison between the supplied electrical power and the received hydraulic power of this pump. and of this system. So I'm going to use valve 103 to adjust my flow rate at 24 volts to my maximum of 400 liters per hour. Using voltage as my independent variable, I'll reduce the voltage by 2 volts at each data point, and at each data point I will record the voltage, the current, the pressure, and the flow rate. When we recorded our data points, we can see that our volumetric flow rate was in liters per hour and our pressure was in bar. However, we want to be able to produce our hydraulic power in terms of watts. Thus, we're going to need to convert our volumetric flow rate and our pressure into appropriate units to give me watts. Now, since watts is an SI unit, that means that my volumetric flow rate would need to be converted to meters cubed per second, and my pressure would need to be converted to pascals. In order to do that, I'll start with my pressure because it's the easier of the two. I'm going to get pressure in units of bar. And in order to convert that to pascals, we simply have 100,000 pascals per bar. And that will give me units of pascals. In order to convert my volumetric flow rate, this one's a little bit more complicated. I'm going to start with liters per hour. And I'll have to convert my hour to seconds. So 1 hour has 3,600 seconds. And looking at liters, 1 liter is 1,000 milliliters. And 1 milliliter is the same as 1 centimeter cubed. And 1 cubic meter is the same as saying 100 centimeters cubed. And that will give me units of meter cubed per second. Now, if we want to check and make sure that our power is going to, in fact, give us watts, you can do that analysis as well. So if I want power to be in watts, I know that power is defined by the equation for hydraulic power, the pressure multiplied by the volumetric flow rate. So I am going to get pascals times meters cubed per second. And we can recall that a pascal is a Newton per meter squared, as it's a pressure. And I'm going to multiply that by a meter cubed per second. So the meters on the bottom are going to cancel out, and I'm going to be left with just the 1 meter on the top, giving me Newton times meter per second, which is the same as saying a joule per second, which is, in fact, a watt. Now, to show some of my unit conversions, my first measurement of volumetric flow rate at 24 volts, Q equaled 400 liters per hour. So working that out, 1 hour, 3,600 seconds, times 1 liter over 1,000 milliliters, 1 milliliter to 1 cubic centimeter, and 1 cubic meter to 100 centimeters cubed. And this will give me a flow rate of 0.000111 meters cubed per second, which is the same as saying 111 times 10 to the negative 6 meters cubed per second. If I want to convert my pressure, the first pressure reading was 0.29 bar. So I have 100,000 pascals per bar, which will give me 29,000 pascals. Now, computing my hydraulic power, going to have our pressure multiplied by our flow rate, so 29,000 pascals times 111 times 10 to the negative 6 meters cubed per second. And that yields a value of 3.219 watts. Looking at my electric power, this is going to be my voltage multiplied by my current. So at this same reading, we had 24 volts. And my current was 0.795 amps. This gives me a power of 19.08 watts. So we can see that we do not have a very efficient conversion of power from our electronic power to our hydraulic power. In order to look at that efficiency, our efficiency is defined as P out over P in, or in this case, P hydraulic over P electric. So that gives me 3.219 watts divided by 19.08 watts, or an efficiency of 0.1689 or 16.9%. For this section of the laboratory, we're going to be simulating on-off control, and we will be trying to keep our set point at 2 liters on the upper tank, and I will be varying the withdrawal rate for this. what is on-off control? On-off control is a digital version of closed-loop control, wherein we are controlling the set point of our system, or we're controlling keeping our system at our set point rather, by turning on and off our actuator. We're not using continuous control, so it's a very simple system, and it is pretty simple to implement. It's overall usually a bit cheaper to implement, but of course it's not going to give you maybe as accurate of a control system as you would be able to obtain with, say, a PID loop. But for the basics, I'm going to have an axis, is that over here? An axis to define my controlled variable. In this case, my controlled variable is going to be level in tank. And I set mine to be 2 liters. This is my set point. And this is going to be my time. So I'm going to be plotting this variable with respect to time. And so I have my set point. And that's what I'm trying to actually maintain. Now, if I turn this on, I'm going to have some slope upward. And this is going to be the rate at which the tank is filling with respect to how fast the pump can push water, and also how fast I am withdrawing water. So this rate is going to be affected by how fast I am withdrawing water, so that slope will change. But at some point I have to decide to turn this thing off. Now if I decide I'm going to turn it off right here, well, it's going to need to turn right back on because it's going to be right outside of that range. And you can see I would have to just like continually turn that on and off basically as fast as the actuator could. What's this going to result in? It's going to result in you wearing out your actuator and premature failure. So we don't want to do that. So what we do with on-off control is we set points. Get my blue ink. There we go. We set points. So arbitrary. Upper threshold. And lower. Hey there, doesn't look right. Alright, and lower threshold. So instead of having this oscillation that it's constantly turning on and off, yeah, we're going to turn it on and we're going to turn it off, but we're going to do it a lot more slowly and a lot less often. So we would continue up. I'm going to let it drain. I'm going to fill it. Notice that I'm varying these slopes a little bit. I'm not a very good artist, so pardon. But I'm going to fill. It'll drain. We'll fill. And this doesn't have to be linear. I could be withdrawing at different rates, but eventually I'll get down here and it will have drained to my lower threshold, and then I'll turn back on again. Alright. And I'm out of space, so we're going to call that there. So the major thing to take away here is that, for color. Maybe. The major thing to take away here is that when we get to the lower threshold, we're going to turn on our actuator. And when we get to the upper threshold, we're going to turn off our actuator. And that's on-off control, simple as that. All right, I'm going to do the best that I can to demonstrate continuous control on the tank system here. I'm going to try to keep the level at 2 liters. Unfortunately, my power supply has a tendency to lock the voltage if I haven't touched it in, a few seconds, which is not really appropriate for this demonstration, but it's the only one that I have at the time. So it's what I'm using, and we'll do the best that we can. But so I'm going to turn this on, and I've got it set to 24 volts. And I'm watching my system fill. And I'm getting closer to 2 volts, so I'm going to start ramping down my current. But it's not quite getting there, so I gotta turn it up a little bit more. Oh, but I overshot. So I need to turn that down. But now I'm under. And that is just about 13 volts, or that's exactly 13 volts, and that is just about perfect. I do have a little bit of a steady state error, and I am climbing a very little bit, so I would have to adjust this in. I can't adjust it in smaller increments. About 12.6, and that's staying pretty stable. So we're going to say that currently my steady state value with this withdrawal rate is 12.6 volts on this motor. And my system would eventually come to that, and it would eventually balance out at that point. So we call this steady state. Now what happens if I change my withdrawal rate? Well, now I no longer need that much power. I'm going the wrong way. Alright, we're going to call that about 11.5 volts. So we can see that now, since my withdrawal rate changed, of course my steady state value is going to change. And our goal in continuous control is to try to make that process happen as quickly as possible. So we want to be able to quickly fill and correct that error, but we don't want to have all of this nonsense. We want to get there as quickly as possible, but we also don't want to overshoot, and we want to keep it at that level. Continuous control does not have to be accomplished using a PID controller, although it is the most common application. But what we're demonstrating here is just the concept of continuous control. So we're looking at this not in terms of a PID control or anything else, we're just looking at the dynamics of the system. Alright, so again, I'm going to have an axis representing my controlled variable. Which in this case is tank level. And I'm going to have my set point. Again, I'll set this at 2 liters. It's arbitrary, but now my set point. And again, I'll just show my axis with respect to time. So in this case, we're going to start out pretty much the same as we did with on-off control. So my tank is empty. And I have a huge error in this. I want to get to my set point as fast as possible, so I'm going to turn on my pump as hard as I can. And I'm going to get there, but then I'm going to turn it off, and I'm going to overshoot a bit. And so gradually, I will stop overshooting as much and I'll balance out. Now, if we, for instance, don't turn our pump on as hard, we may look something more like, oh, we're eventually gonna get there. Something more like this, as we gradually ramp down our voltage on our pump until it turns off. So we can see with our continuous control that we're going to have a curved response, whereas we had a mostly linear response with our on-off control. And that kind of makes sense because we're only adjusting the slope one time for an on-off control, whereas here we can continually adjust the slope of the filling curve.